Hello everyone, good morning. We don't have much time to go for the interaction. So yes, within 30 minutes we are going to give a quick revision in all syllabus. So yes, without further delay, let's get started. So here comes the first chapter, that is solution. So in solution you can see the most important question, that is Henry's law, and this is the statement of Henry's law. You can see it states that the solution of two volatile liquids, the partial vapor pressure of each component is directly proportional to the mole fraction. So make sure whenever you are writing this type of thing, then you are mentioning the abbreviation. Okay, P equals to kH of X. So what is P? That is a partial pressure. What is kH? That is a Henry's constant. What is X? That is a mole fraction. So you have to mention them, make sure, don't forget it. Okay, so next, state Henry's law and write its mathematical term. What is the significance of kH? Application of Henry's law. So the same question I told you already, here you can see. Okay, so now we are going to discuss significance of kH. So higher the kH value, less the solubility, because they are inversely proportional. Next you can see application of Henry's law. If you go through, then it is used for the preparation of the carbonated beverages. It is used for the scuba divers for the respiration to avoid bends. Next, to maintain the climber's respiration at the higher altitude. As the pressure decreases, solubility of O2 in the blood decreases, right? That is called anoxia. Next, ideal and non-ideal solution. As you can see, this is the difference. One like ideal solution, it obeys Raoult's law. Non-ideal, they do not obey Raoult's law. Delta H mix equals to 0, delta H mix not equals to 0, delta V mix equals to 0, delta V mix not equals to 0. Interaction, it's very important. AB interactions are equal to AA and BB interaction, and for that case AB interaction are not equal to AA and BB interaction. Example you can give out of it. Okay, so example you can give the homologous series like N-hexane and in, let's say, heptane. Okay, for that case you can give the example of ethanol plus acetone. Okay, next let's go ahead. Azeotropic mixture. So it's a binary liquid mixture having the same composition in the liquid and the vapor phase. Okay, one example you can take the example of ethanol. Okay, ethanol 95% ethanol and 5% H2. Okay, and they can be of two types, that is maximum and minimum boiling azeotrope. Okay, so these are the difference between maximum and minimum boiling azeotrope. That is also important. One shows negative deviation, another shows positive deviation. Maximum boiling azeotrope, they boil at higher temperature than that the each component, than the boiling point of each component, right? And for the minimum boiling azeotrope, they boil at the lower temperature than that of the boiling point of each component. Example you can give. Next, these are the formulas, very important. Last moment you just go through the formula once. This is for the relative lowering of vapor pressure. This is for the elevation of boiling point. Okay, this is the same thing here for the diluted solution. This is for the diluted solution. Okay, both of them are relative lowering. This is the depression in freezing point. This is the osmotic pressure. Very important formulas. Okay, next let's go like what is osmotic pressure, give equation, and what is reverse osmosis. So here you can see what is osmotic pressure. Whenever external pressure is applied on the concentrated solution to stop the osmosis. Okay, means some pressure you are applying that is more than that of the osmotic pressure. Okay, so that is basically osmotic pressure. Next equation, I guess you know, pi equals to CRT. Okay, that is the equation. What is pi, what is C, what is R, what is T, that you have to mention here. Okay, next, what is reverse osmosis? So that is the pressure, when a pressure more than that of osmotic pressure is applied on a concentrated solution, then what happens? Solvent flows from the concentrated solution to the diluted solution, concentrated to diluted. Okay, so through semi-permeable membrane, definitely this phenomenon is reverse osmosis. Okay, so here one more question, that is desalination of water. Desalination of seawater. one of the application, it's important. Okay, so yeah, let's go forward. Next, 3 reasons to justify osmotic pressure method has advantage over the colligative methods. So what is this? Basically, first it uses the molarity, right, instead of molality. All the colligative property, if you see, they use the molality term, but here they use the molarity. Okay, now it can be measured in room temperature, because whenever you are having the other colligative properties, they will be having temperature variation, right? So they will be having the room temperature analysis, so it's easier for the biomolecules to sustain. Next, magnitude is large as compared to that of the colligative properties. I guess it's clear. Let's go ahead. Explain the desalination of water by reverse osmosis. I just discussed about it. You can see reverse osmosis is used in the desalination of seawater. So what we do, pressure more than that of the osmotic pressure we put, definitely in the room temperature, almost 30 atmospheric pressure we put. Okay, then what happens? Pure water squeezed out of, like pure water squeezed out from the sea water, it comes and it, like from here to here, solvent comes. Okay, from the salt water, pure water gets extracted out and it comes towards the fresh water. Okay, so what the membrane we use here, cellulose acetate. Okay, next we will move towards the chemical kinetics. In chemical kinetics, first question, what are the main criteria for the effective collision? You can see activation energy, you can give the example, proper orientation of the molecule. Okay, next, derive the integrated rate equation for a zero order reaction. For your convenience, I will do it in front of you. Okay, so here you can see A gives you product. Okay, I'm really sorry that I'm unable to read out your comments, because we have really less time and we have to cover the entire syllabus. As I told you, only 30 minutes and full syllabus. Let's go. So yeah, A gives P, and from here the differential rate equation, if you want to write, R equals to minus d of A by dt. Okay, this is your equation number 1. Now in accordance to rate law, if you want to write, that is going to be k into a power 0. A power 0 means what? 1. So R equals to k. That is your equation number 2. Now this particular thing I'm not writing, equating equation 1 and 2, what we are getting? Minus dA by dt is equals to k. So from here what I will get? dA is basically equals to minus k into dt. Now I will put the integration. So you can put the integration and you can find out the integration constant value and you can go ahead. But what I prefer is put the limit here itself, that you can follow actually. So whenever t equals to 0, it is A naught, right? Whenever t equals to t, this is AT. Okay, so now if I just further go ahead, after doing the integration, if I put the value, then it should be something like AT minus A naught is basically equals to minus k into t. Okay, just a little bit rearrangement. We can do rearrangement here itself. So k is going to be A naught minus AT divided by t. Okay, so again I'm telling, once you are done, please make sure that you are writing every terminologies, what is k, what is A naught, what is AT, everything you have to mention out there. Okay, now let me show you something. It's not asked here, but I want to show you the graph. Okay, so here you can see from this equation we will find it out. Okay, so what I'm going to write, A naught minus AT is basically equals to KT. Okay, so from there if I just take it that side, AT equals to minus KT plus A naught, right? Okay, so this is the thing is coming just after rearranging a little bit. So this is your y, minus k is your m, this is your x-axis, this is your c, y equals to mx plus c, right? So what is the nature of the graph? It's a straight line. AT versus T, AT versus T graph. The straight line nature is like that. Intercept value is A naught. Okay, and what is the value of slope? That is the most important thing. Slope is basically minus K. So what I said, for zero order reaction AT versus T graph slope, you will get minus K. Okay, let's go ahead. First order. Okay, so let's do it. A gives you P, right? So from there R is basically equals to minus dA by dt, right? Another one, R equals to K into A power 1, right? This is equation number 1, this is equation number 2. What is the writing part I am avoiding? Okay, so what you can do, minus dA by dt is equals to K into A. So let's take them in a single side. So we can do dA by A equals to minus K into dt. So now you put integration. So T equals to 0, A is A naught, right? When T equals to T, then A is AT. Okay, further if I continue, then what I will get? I will get ln of AT minus ln of A naught, right? Ln of A naught is basically equals to minus KT. Okay, so from here see, from this equation I will get the graph. Okay, so again we will do it later. A graph I will show you, all the possible graph from here I will show you, but at first just see how I can derive it, from where like in which form you have to stop. That let me show you at first. Okay, so what I have to do, I have to convert it to log 2.303, right? So log, let's change the sign as well, log A naught minus log AT, right? Equals to KT, right? So from here I can write K equals to 2.303 by T log A naught by AT. So here you have to stop and make sure you are writing the abbreviation. Okay, now let's proceed towards a graph. So from here we will start. Okay, so what I have, ln of AT minus ln of A naught is basically equals to minus K into T, minus K into T. So from here what I'm going to do, ln of AT equals to minus KT plus ln of A naught, right? So here this is my Y, minus K is my M, this is my X, this is my C. So if I draw the graph, what versus what graph? ln of AT, right? ln of AT versus T graph. Okay, I will get the graph nature like that. Wait, I will get the nature of the graph something like this. The intercept value is ln of A naught and slope is basically equals to minus K. Okay, remember this. Okay, and one more thing that I want to tell you, zero order reaction, A naught by T, A naught versus T graph slope equals to minus K. But first order reaction, ln of NT versus T graph will give you slope equals to minus K. I guess this is clear. Okay, let's go ahead. One more thing that I want to do here, so let's convert it to log. We will get second graph. Okay, so we can do it like this, log of AT equals to minus K by 2.303 into T, and here I will get plus log of A naught, right? That is also we can do, right? So now if you draw the graph, be careful about it. Log of AT I am taking log instead of ln. Okay, log of AT versus T graph. Okay, if I take, then also I will get the same type of graph with the intercept log of A naught. Okay, but the slope value will be here. Slope will be something like minus k by 2.303. Be careful about it. So slope value will be minus k of 2.303. Clear? Okay, now you can see one more. Okay, so from here we can do it. Okay, so let's take the log A naught there itself. So log of AT minus log of A naught, okay, equals to minus KT by 2.303. We will change the sign a little bit, like log of A naught minus log of AT, right, equals to KT by 2.303, right? So now what I'm going to do is just see log of A naught by AT equals to K by 2.303 into T plus 0. Plus 0 we can do, right? So now from here what you will get, this is your Y, okay, this is your M, okay, this is your X, and 0 is your C. Means 0 intercept means it is passing through the origin. So if you draw the graph, so what will be the y-axis? Log of A naught by AT. What is the y-axis? Log of A naught by AT. So graph will be something like this, passing through the origin. What is the value of slope? Slope will be equals to, okay, T. Slope will be equals to K by 2.303. That's it. Okay, these three graphs are very important. Okay, I guess this is clear. Let's go ahead. What is the collision frequency? Give the drawback of simple collision theory. You can see the number of collision per second per unit volume of a reaction mixture is called collision frequency. Okay, drawback of simple collision theory. You can just go ahead with this thing. Just go through the things. Okay. So basically what we do, actually we consider them as a hard sphere, okay, structural aspect that we like neglect, okay, and it is supposed to that only the kinetic energy of the colliding molecule contribute to the required for the passing energy barrier. Okay, so there is nothing else. We are not considering rotational or vibrational energy. They are also part of this. Okay, so let's go ahead. Okay, this is the Arrhenius equation. Arrhenius equation, this is the abbreviation, I guess you remember. Okay. Next, explain the effect of catalyst. It's a very important question. Okay, this is the graph you have to do. So you have to start from the reactant. At first you have to show the original diagram. You have to show this is the activation energy without catalyst. But in case you are adding catalyst, you are having this, means activation energy is reduced while using the catalyst, right? So this is the graph you have to draw. Next, using energy distribution curves showing temperature dependence of the reaction. So this is basically the Maxwell-Boltzmann curve. So here you have to show the fraction of molecule versus energy. Okay, so whenever the temperature is T, you can see I had only this much, right? But whenever you are having T plus 10, means you are increasing the temperature by 10, then like more amount of molecule, they are crossing the threshold energy. That's it. Okay, let's go ahead. Okay, so activated complex theory, it's also very much important along with the graph. So basically you can take the example of H2 plus I2, H2 plus I2 through activated complex, it will form the HI. Okay, so through activated complex means in the activated complex, that is at the transition state, means at the top of the energy barrier. At this stage you will get the activated complex where it is neither the reactant nor the product. Okay, so it's a very unstable complex. Okay, let's go ahead. Electrochemistry. Okay, so here comes few questions like direct measurement of conductivity of ionic solution by Wheatstone bridge is not possible. Give reason. Suggested remedy to solve it. Okay, so first is direct current will change the composition of the ionic mixture. Okay, next, solution cannot be connected to the bridge. Okay, Next, next you can take that like instead of connecting, next question, next part, instead of connecting in connecting the direct current, alternating current should be passed through it. That is a solution, okay, as a remedy you can tell. And electrolytic solution is connected through Wheaton bridge by using conductivity cell. Okay, let's go ahead. Faraday's first and second law of electrolysis, you can see, I guess you remember that, you had been through it. Just for a quick revision you can go through, like the amount of substance deposited or liberated at any electrode during the electrolysis is proportional to the quantity of electricity passed. Okay, write the equation m equals to z into I into t. What is m, what is z, what is I, what is t, that you have to mention there. What is second law? Second law is basically when same amount of electricity is passed through the different electrolytic solution, the masses of the substances that is deposited or liberated at the different electrodes, they are directly proportional to their electrovalent mass. Okay, I guess this is clear. Let's go ahead. Okay, so here comes whenever electrode potential, which factor they are depending, metallic conductance, which factor they are depending, ionic conductance, the factor depending. Okay, see, electrode potential, they are depending upon the ion concentration, temperature and electrode material. Okay, if you are having metallic conductance, okay, if you are having metallic conductance, it depends upon the nature of the metal, nature of the structure of the metal, okay, and number of valence electron present over there, and also temperature. Next, ionic conductance. Ionic conductance depends upon the nature of the electrolytes, okay, temperature, okay, nature of the solvent, means if it is viscous or not, okay, concentration of the ions, next, size of the ions, okay. Now factors affecting the conductivity, nature of the electrolyte again, temperature and pressure, okay. Next, products of electrolysis. Products of electrolysis, they are dependent upon the nature of electrolyte again, type of electrode that you are using, standard electrode potential, next, concentration of the electrolytic solution and over voltage. Okay, let's go. This is the dry cell, I mean anodic and cathodic reaction. You can see zinc will form Zn2 plus and 2 electron. That electron will come to the cathode, MnO2 is there, right, and NH4 plus is there, that will form MnOH, okay, plus ammonia. Okay, I guess it's clear. Next, explain the role of produced ammonia. Ammonia produced in the reaction, it forms the complex with Zn2 plus. Okay, next, explain the construction of standard hydrogen electrode. Okay, so diagram is very much mandatory here. Maybe you can draw it with pencil or pen, but diagram should be there. So try to draw the diagram at the right side, at the right corner of your paper. Okay, so what we use basically, you can check out from here. Okay, it consists of a platinum foil coated with finely divided platinum. Okay, now this foil is connected with platinum where? With mercury. Okay, now copper wire is connected from mercury to, like it is getting out for the external circuit, right. Now this platinum foil is dipped in 1 molar HCl. Just look at this diagram. At first you draw the diagram, then explain it. So what is there basically, what is there in this particular square? You can see this is basically platinized platinum, that's it. So platinum coated platinum, okay, that is connected with mercury. This is a mercury. Okay, this mercury is basically outside, you can see external circuit it is making. Okay, so now what we are doing, we have inlet, from inlet we will pass hydrogen gas. Okay, so on the platinum surface the hydrogen gas will be adsorbed. Okay, next you can see, write the reaction. What happens basically, H plus will takes up electron and it forms half of H2. Okay, next, what is the symbolic notation of the electrode? This is this one, platinum hydrogen gas slash H plus 1 molar. Right. Next question, platinized platinum is used for the construction of SHE that provides the surface area for the hydrogen gas absorption. Okay, next, draw the neat and level diagram of H2O2. So this is your H2O2 fuel cell, anodic and cathodic reaction. In cathode what happens, oxygen gas gets reduced, oxygen gas gets reduced, and in anode what happens, hydrogen gas gets oxidized. Overall reaction, if you just add them, you will get the overall reaction. Okay, Okay, let's go ahead. Effect of dilution on conductivity and molar conductivity. So conductivity always decrease with decreasing the concentration of both weak and strong electrolyte. Okay, because why? If you just dilute the solution, the number of ion, okay, like with the volume, with in unit volume, that will decrease, right? But if you talk about the molar conductivity increases with decrease in concentration. They are inversely proportional, because whenever you are talking about the molar conductivity, total volume also increases, right? So that is the thing. So total volume also increases. So it has been found that dilution of the solution increases the volume, dilution of the solution increases the volume, right? So as a result of this increased volume, that decreases the molar conductivity. Okay, let's go ahead. Okay, write a cathodic and anodic reaction of the lead storage battery. You can see in the anode what happens, lead gets oxidized. It forms Pb2 plus, means PbSO4. Okay, and in cathode lead gets reduced. Okay, so overall cell reaction is like this. Next you can see state Cold-Rush law. So you can see Cold-Rush law, it basically states the molar conductance of an electrolyte at infinite dilution, that is equals to the sum of the ionic conductance of the individual cations and anions of the electrolyte. Okay, next give two application are similarly it's used for the determination of the conductivity of weak electrolyte, okay, and the extent of dissociation. Next, D and F block. Okay, study of actinide element is difficult. Give reason, because they are radioactive, okay, very short lived, and could not be, they can be prepared in only nanogram, very small amount we will get. Next, explain the catalytic properties of transition metal, that is variable oxidation state, okay, large surface area. Okay, next, incomplete or tertiary filled d orbital, formation of intermediate compound. Okay, one example you can give vanadium pentoxide. Next, lanthanide contraction, you know, gradual decrease of like atomic and ionic radii. What is the reason? That is a pure shielding of d and f orbital. Next, give any two consequences, that is basically the atomic radii of 3D and 4D series, they are so close to each other that we can't separate. Okay, and basicity decreases from lanthanum to lutetium. Next, potassium dichromate manufacture, be careful about the thing. So first chromite will be infused with Na2CO3, then Na2CrO4 is treated with acid, it forms Na2Cr2O7. Na2Cr2O7 further it is treated with KCl. Okay, so be careful about the balanced equation. You have to write the balanced equation. This is the most important question and you can expect it in your upcoming examination. Yes. Next, again, KMnO4 preparation, it's also very much important. Okay, MnO2 is fused with KOH, you will get K2MnO4. Okay, then MnO2, then again, that K2MnO4, that further being like treated with hydrogen, you will get MnO4 plus MnO2 plus water. Okay, KMnO4, I mean KMnO4 plus MnO2 plus water. Okay, next, lanthanoids and actinoids, if you just see, this is the difference. Okay, one case it is entering into 4f orbital, another case it is 5f orbital. Okay, lanthanoids are non-radioactive, they are radioactive, like this you can go ahead. Okay, any two difference. Next, what is the composition of mish metal? So lanthanoid 95% plus iron, almost 5%, and traces of some sulfur, carbon, aluminium, this can be there. It is used to prepare the bullets, shell and lighter flint. Okay, go ahead, calculate the magnetic moment of Sc3 plus. I'm not going ahead with the calculation and all. You know the electronic configuration, you know how to find out the number of unpaired electrons. So then magnetic moment equals to under root n into n plus 2. Go ahead with the formula, the answer you will get in Bohr magneton. Okay, next, calculate the spin only, the same thing only. Okay, explain the formation of interstitial compound. So what happens basically if small atoms like hydrogen, carbon, nitrogen, if they get trapped, okay, into the lattice, crystal lattice of the metals, like with titanium, with manganese. Okay, like with titanium they can form TiC, with manganese they can form Mn4C. So this type of metal, they are called interstitial compounds. So they have the properties, different properties like high melting point, they are chemically inert, highly conductive. Okay. Next, transition metal forms large number of complex compound. What is the reason? Smaller size. Next, larger ionic charge. Okay, or like they can polarize the ion, they can polarize the negative charge nicely. Okay, so high charge to ratio, high charge to size ratio. Okay, next, availability of definitely vacant d orbitals. That's it. Okay, next, coordination compound, Warner's theory. You can see, you can just go ahead with the primary valency, secondary valency. Okay, you can explain how they can be satisfied. Okay, and you can discuss about the secondary valency, that it have the characteristics to give the spatial arrangement to the metal, not to the metal, to the entire complex. Okay, and coordination number also you can explain over here. Next, okay, this is the application of the coordination chemistry. Okay, you can just go through hardness of water can be removed by EDTA, extraction process, purification of metal, in different kind of, you know, biological process like photosynthesis. Okay, in our body, hemoglobin, it is a magnesium complex, right? Next, you can take the example of vitamin B12. Okay, so this type of thing you can go through. Next, draw the geometrical isomerism. So for this case, first one you will see facial and meridional. Let me show you. Okay, for this you will see facial, right? Okay, this is your facial. Okay, this is your meridional. If I draw the meridional, okay, this is your meridional. Okay, next, for the second case, if I draw, okay, for this case you will get cis trans, but cis is optically active here. Okay, let's draw the cis, let's draw the trans at first. Okay, PT, this is EN, Cl, here also Cl, this is your trans. Okay, okay, so if I draw the cis, it will be something like this. Okay, now draw the optical isomer of it. So PT, Cl, Cl. Okay, so this is basically, let's take D, this is L. Okay, I guess it is clear to you. Let's go ahead. Okay, now define ambidentate ligand, heteroleptic complex, and chelating ligand. Ambidentate ligand means they have two donating side, but they donate from one side at a time. Okay, you can give the example of cyanide. Heteroleptic complex means like in the coordination sphere you will be having more than two type of ligand. Okay, if the metal is connected to more than two ligand, two type of or more than two ligand. Okay, chelating ligands means if di or polydentate ligand, they use their all the donating side simultaneously. Okay, two or more than two donating sides simultaneously. Okay, you can give the example of EDTA. Next, synergic bond. So that is basically that you can explain that with S and P character both. At first, metal to carbon to metal, they can form the sigma bond. For carbonyl, we can explain they can form sigma bond. Then what happens from the metal? They gives back the electron cloud to the carbon, right? To the carbon pi star anti-bonding, right? So that is basically synergic bond. So S character and P character both. Let's go ahead. Limitation of CFT and VBT, you can just go through. Basically VBT sometimes cannot explain the magnetic character. Okay, thermodynamic and kinetic stability they cannot explain. Okay, this type of thing you can give. Limitation of CFT, you can see they consider ligand and metal as a point charge, and they do not consider the covalent character of the metal. Okay, metal ligand bond. Next, This is the octahedral and tetrahedral splitting. You can see, just remember, while you are doing the tetrahedral splitting, T2G below, EG up. While you are doing the this is octahedral, this is tetrahedral. Whenever you are doing tetrahedral, E below, T2 up. Okay, that thing you have to remember. Let's go ahead. Hybridization of this complex. CO is basically what? CO3 plus. This is basically 3D6 system. So if I draw 3D, 1, 2, 3, 4, 5, right? This is your 4S, this is your 4P. So this is 3D, 4S, 4P. Okay, so 1, 2, 3, 4, 5, 6. Initially it was like that, so but later on pairing takes place, right? So once the pairing takes place, forced pairing of electron because of the presence of strong field ligand. Okay, it will look something like this. Okay, now what happens? Inner d orbital and outer s and p orbital will hybridize to form D2sp3. Okay, and here you know the ammonia will give the lone pair, all of them. Okay, I'm not writing all of them. So this is basically give you the octahedral geometry, and you can see no unpaired electron, hence you can say diamagnetic. Okay, I guess it is clear. D2sp3 is the geometry, octahedral and diamagnetic in nature. Okay, let's go through. This is your biomolecules chapter. What are hormones? Name the hormones responsible for the external stimuli. Okay, so here you can see like hormones that together regulate the sucrose level. That also I guess you know, that is a insulin and glucagon, right? Now what are hormones? They basically intracellular messenger. Okay, they are secreted from the endocrine glands. Okay, and directly it goes to the bloodstream. Okay, next you can see these are the different types of hormone and their functions. Like, let me just tell you a little bit as a revision. Glucagon is basically, it increases the blood glucose level. Insulin, they maintains the sugar level in the blood. Epinephrine and norepinephrine, the responses for the external stimuli. Okay, next thyroxine, it is produced by thyroid gland. It is basically iodinated derivative of amino acid of like tyrosine. Okay, now if you are having low concentration of thyroxine, you will be having hypothyroidism, that is the you will see the obesity. Okay, and high concentration means hyperthyroidism, you will see the enlargement of the thyroid gland. Here you can see we have more steroidal hormone, right, that is produced by adrenaline cortex and gonads. So glucocorticoids, mineralocorticoids. Okay, so glucocorticoids is basically released by the adrenaline cortex. Okay, it controls the controls the carbohydrate metabolism. Okay, modulate the inflammatory reaction. That's it. Mineralocorticoids is what? It controls the excretion of water. Okay, what is Addison's disease? If you are having malfunction in the adrenaline cortex itself. Okay, so it can lead you that weakness, different type of like stress, hypoglycemia, this type of thing. Okay, let's go ahead. Testosterone, estradiol, progesterone. Testosterone is basically released by gonads. Secondary, it develops the secondary male characteristics, the voice, facial hair, those things. Estradiol is a female sex hormone. It's basically development of the secondary female characters like a menstrual cycle. It controls a menstrual cycle and all. Progesterone. Progesterone is basically responsible for the preparing the uterus for the implantation of the egg. Okay, let's go ahead. Okay, structure of sucrose and maltose and lactose. Do coffee. Structure of sucrose, maltose and lactose. Okay, so basically here you can see this is the sucrose structure, this is the lactose, and this is the maltose structure. So just remember, sucrose is basically alpha D glucose plus beta D fructose. Next, lactose, both of them are beta D glucose, for lactose is beta D galactose and beta D glucose. For maltose, maltose is basically alpha D glucose and alpha D glucose. Okay, let's go ahead. Essential amino acid and example. What are the essential amino acid? They cannot be synthesized in the body. You have to take them through diet. Lysine, valine, leucine. Okay, next, how does glucose react with HI? Okay, so these are the reaction. You can see this is the reaction with HI. You will get a N-hexane type of system. Next, how it reacts with oxime, it reacts to form glucose oxime type of thing. That will tell you the carbonyl compound is there. Okay, carbonyl group is present there. Okay, this is basically reaction with acetic anhydride. That will tell you 5-OH group is present, and this is basically bromine water reaction. That will give you the gluconic acid. That will tell that the carbonyl that is present, it's nothing but the aldehyde group. Okay, let's go ahead. Denaturation of protein, it's basically losing biological activity of protein. Okay, so 1 degree structure, they remain intact. Okay, next, going ahead, vitamins. So these are the all vitamins and the related disease. Vitamin A, we can get it from fish liver oil, carrots, butter, milk. Okay, we can in deficiency of vitamin A, we can have xerophthalmia. Okay, night blindness. Vitamin B1, that is thiamine, we can get it from, you know, green vegetables, milk. Okay, we can get berry. Okay, next, vitamin B2, that is riboflavin, that is we can get it from milk, egg white. Okay, next we can like digestive disorder, burning sensation, this type of thing we can get out of it. Next, vitamin B6. Okay, that also we can get from the yeast, milk. Okay, so that will give you the convulsion in case it is taking like we are having deficiency of it. Okay, vitamin B12, we are having like anemia type of disease. Okay, vitamin B12 from where we can get meat, fish, egg, etc. Vitamin C, there is ascorbic acid, citrus fruit is the source. Absence of this or deficiency of this can give you the bleeding gums. Okay, vitamin D, there is a exposure of sunlight, egg yolk. Okay, and deficiency can give you ricket. Okay. Okay, let's go for the haloalkanes and haloarenes. Here you can see these reactions are important. So yeah, first one you can see this is the Woods-Fittig reaction. Sorry, this is a Fittig reaction. You can see both the benzene ring will be attached here. Remember the reagent in this case. Okay, so this is your which reaction? This is a Schwarz reaction. Okay, so Br will be replaced with fluorine. Next, if I go ahead, alkyl iodide, it's often prepared, that is basically the Finkelstein reaction. So basically if you are having, let's say, CH3 Br, and if you are giving NaI in dry acetone, right? It is a very important reaction. Dry acetone if you give, you will end up with CH3I plus NaBr. That's it. Okay, this is the Sandmeyer's reaction. When you are having like aniline, it will react with the nitrous acid in 0 to 5 degrees Celsius. It will form benzene diazonium chloride, right? That is N2 plus Cl minus. Then in presence of CuCl, HCl, this reagent I am taking, or Cu2Cl2 you can take. Remember that oxidation state of copper must be +1. This will be chlorine only, right? Plus nitrogen and all you will get. Okay, these are the byproducts. Let's go ahead. Said-Zeff rule. What is the Said-Zeff rule? Said-Zeff rule is basically most substituted alkene will be the major product. So whenever, let's say you are doing this type of reaction, let's say this type of reaction, so you can get hydrogen CH3, here I am having CH2, here I am having CH, here I am having CH3. Okay, so you can end up with this type of product, CH double bond CH, here CH3, right? Wait. Okay, whenever you are treating this with alcoholic KOH. Right, one more thing, this is also beta halogenation. Another thing you can get out of it is basically CH3, here CH2, here CH double bond CH2. But this particular alkene is basically more substituted. Okay, hence this is the product I will get. So make sure that you are giving this example. Let's go ahead. Aryl halides are less reactive towards nucleophilic substitution. Why? Because of the resonance effect, and sp2 hybridized carbon. Resonance effect will give you double bond. Okay, partial double bond like character, and sp2 hybridization will give you the more s character. Okay, so bonds are strongly held. Okay, next you can see this is the SN1 mechanism. So carbocation formation, it's a very important question. Okay, so carbocation will be attacked by the nucleophile and you will end up with a tertiary butyl alcohol. SN2 mechanism, here bromine will leave transition state, penta coordinated transition state will form here, and you will end up with the alcohol. Next, alcohol, phenols and ether. So preparation of phenol from cumene, this is a reaction, this is a cumene in presence of oxygen, it will form cumene hydroperoxide, from there phenol plus acetone, important. Okay, next Williamson ether synthesis. If I just go for the reaction, then let's say RO minus Na plus. Okay, now I am having one alkyl R prime halide, alkyl halide. So these will attack here, this will go. So this is basically one SN2 type of mechanism, and you will end up with RO R prime. Okay, this is your ether. Let's go ahead. What is Lucas reagent? Okay, Lucas reagent is what? ZnCl2 plus H2SO4. So 3 degree will give you instant turbidity, right? Instant turbidity. 2 degree, if you go ahead, 2 degree will give you turbidity in 3 to 5 minutes. Okay, and 1 degree alcohol will give you no reaction. Okay, let's go ahead. Orthonitrophenol is steam volatile but not paranitrophenol. The reason is basically hydrogen bonding, intramolecular hydrogen bonding. How I can separate? Steam distillation. Go ahead. Cole's reaction, how do you convert phenol to salicylic acid? This is the reaction you can see. Okay, go ahead. Reimer-Tiemann, this is the Reimer-Tiemann reaction. Phenol alumine treated with CaCl3 and NaOH, you will end up with salicylaldehyde. Let's go ahead. Catalytic hydrogenation of alkene, very important, 3-step protonation of alkene you can see. Next step is attack by H2O, nucleophilic attack you can say. Next, deprotonation. Okay, all the 3 steps are important. Dehydration of alcohol, very important. First, protonation of alcohol group, then removal of protonated alcohol to give you carbocation. This is the slowest step. Next, removal of hydrogen. Okay, elimination. Next, aldehyde ketones and carboxylic acid. If we go ahead, that is between methanol and ethanol, how you should separate. Sorry, how which one will undergo aldol condensation? So definitely ethanol will undergo aldol condensation because it is having alpha hydrogen in it. Okay, chemical reaction involved in it, you can just go through one of the aldol condensation reaction. Okay, next. Although phenoxide ion has more number of resonating structure than that of the carboxylate ion, carboxylic acid is stronger acid. Why? Because in phenoxide ion the negative sign comes on carbon, but in carboxylic acid the negative sign comes on oxygen, right? That is more stabilized. Next, okay, HBZ reaction, here you can see you will get alpha halo carbonyl compound. So if I just draw this thing COOH, so now if you give, let's say Br2 in presence of what? Red phosphorus, and water if you give, then you will get this type of thing. Okay, alpha halo carboxyl Br, sorry. Okay, alpha halo carboxylic acid you will end up with. Next, okay, so let's go ahead with this question. This is a very important question. This is basically nucleophilic attack in the, or HCN attack in the carbonyl compound. So if CN minus attacks over there, this bond will open and you will end up with a tetrahedral intermediate. Further protonation will give you cyanohydrin. Okay, next, aromatic carboxylic acid does not undergo Friedel-Crafts reaction. Why? Because the carboxylic acid groups are highly deactivating group. Okay, so it actually, we are using the catalyst, right? Like the catalyst, that is the aluminum chloride. Okay, so it acts as a Lewis acid and gets bonded to the carboxylic acid group itself before it performs the reaction. Okay, let's go ahead. These are the name reaction that you have to remember. You can see Rosenmund, Stephen, Etard, Clemenson, Wolff-Kishner, Aldol, Carnizaro, Haloform, Reimer-Tiemann, Getterman-Koch, HVZ, haloform, decarboxylation, tolerance and filling test. As you can see, we almost got over like 30 minutes. Let me just go a little bit ahead so that I can just clarify a little bit with the reagent as well. So for the Rosenband, what is the reagent? Tell me the reagent in the comment section. Palladium in BaSO4, right? And hydrogen you have to give, right? Stefan's reaction, what is the reagent? SnCl2, right? SnCl2, HCl, right? Next, ATARD reaction, not ATARD, okay? CrO2, Cl2, right? Clemenson reduction, okay? Tell me the reagent. That is basically zinc amalgam, HCl. Okay, Wolff-Kissner, we use hydrazine, NH2. Aldol, we use diluted NaOH, right? Cannizzaro, concentrated NaOH, right? Next, haloform, when you will see, when I am having one methyl ketone, right? One methyl ketone unit should be there, right? Okay, aldol, let me tell you, alpha hydrogen present. Next, Cannizzaro, alpha hydrogen absent. Okay, Raymathyman. Okay, Raymathyman reaction, just now we did Raymathyman and Kolb's reaction. I'm not going through it. Gatterman-Koch, CO in presence of AlCl3 like that. HBZ also we did. Haloform just now we did. Decarboxylation. We can use soda lime. NaOH plus CaO. Okay, next. Okay, next is tolerance and filling test. Tolerance, if I just go ahead, tolerance is basically ammoniacal silver nitrite, right? So ammoniacal AgNO3. Okay, for the fillings test, what we can give? We can give, it is a mixture of fillings A and fillings B. Right, fillings A solution and fillings B solution. So fillings A is basically CuSO4 solution, okay, and this is basically alkaline Rochelle salt. I'm just writing R salt. Okay, that's it. If you remember this much, it will be more than enough. Okay, so here you can see amines. So how do you distinguish between primary, secondary and tertiary amines using Hindenburg reagent? So you can see this is the Hindenburg reagent. Formula is very important. With the primary amine, the thing that compound you will get, that is soluble in alkali. The secondary, it is not soluble, it is like partially soluble in alkali, or it will take some time for the solubility. Next, if you see tertiary amine, they do not react. Okay, next, going ahead, benzene diazonium chloride reacts with phenol, in which the phenol molecules in the para position. Okay, so basically this is your para hydroxy azobenzene type of reaction. So this is a diazocoupling reaction. Okay, benzene diazonium chloride with phenol. So remember, you need alkaline medium for that. Okay, this is the Gabriel phthalimide reaction. Okay, it's a very important reaction. You should go through the mechanism. Next, Hoffman bromamide reaction. This is the Hoffman bromamide, RCONH2 in presence of Br2 and NaOH. You will get RNH2, one carbon less. Okay, so name reaction that you have to go through: Hoffman bromamide degradation, Gabriel phthalimide, carbylamine, Hindenburg. Very important. Okay. So yeah, that's it. I guess your exam will be good. So all the very best. Yeah, it took little more time than that of the 30 minutes, but I guess this is of your own benefit. So yes, make sure that you are watching this, like if whoever is a late riser, they are also watching this video. Okay, so thank you so much for waking up for me, waking up for this live session. Thank you so much. All the very best. Your exam will be all good. So keep calm, relax. You are prepared enough. Always remember, confidence wins in the board examination. Thank you.